Hi there. In today's lecture, we're going to be going through conic sections briefly. So this won't cover everything, so please make sure that you go through the notes as well to get a full coverage of this section. Okay, so we're going to be going through what is a conic section, the different types of conic sections, the vertices and foci of the different conic sections. Okay, so there's a few extra things, and then that will be in the notes. Okay, but this will be the more important stuff for assessments and tests and so on. Okay, so firstly, the different types of conic sections. So I briefly went over this in the previous lecture, but a conic section is found by taking a cone, okay, so something like this, and cutting it at various angles. So if we make a horizontal cut like this, then the cross section over there will be a circle. So imagine taking a cone, cutting it horizontally and looking down, we get a circle. Then if we make a slightly angled cut and look down, we end up with a ellipse. Okay, so slightly elongated circle. Next, if we make it the angle more like this, we end up with a parabola. And finally, a cut, something like that. If we again look at the cross section, we end up with a hyperbola. Okay, so we end up with these different shapes by taking cross sections of a cone, hence conic section. Okay, and the way that we describe, where we are in this list. So on the one side we have a circle, and then on the other extreme we have a hyperbola. Going from one to the other, we differentiate them using what's called the eccentricity. So we differentiate between these conic sections using the eccentricity. Okay, so the eccentricity is just a number that we can calculate, and then that will tell us where along the list we are. So just as a quick example, if the eccentricity is 0, then that means it's a circle. If the eccentricity is 1, it's a parabola. If it's between 0 and 1, it's an ellipse. If it is greater than 1, then it's a hyperbola. Okay, so depending on the eccentricity value, we have a different conic section. Okay, so we can summarize all of this in a nice table. So we have the conic section, the eccentricity, and the equation, so that we can plot these. Okay, so the first one is a circle. It has an eccentricity of 0, and the equation is just x squared plus y squared equals a squared. So a is just some other parameter, and then of course we know that that's going to be the radius of the circle. Okay, next one up, we have an ellipse. Okay, so that's the oval or stretched circle. This has an eccentricity e, given by the square root of 1 minus b squared over a squared. We'll get to those values now. These b squared and a squared, they come from the equation x squared over a squared plus y squared over b squared is equal to 1. Okay, so we can get these values from the equation, and then later on we'll see the geometric origin of these values. And we can see here for an ellipse, if a equals b, we end up with an eccentricity value of 0, which will be a circle. So that's roughly the width and the height of the ellipse is equal, so we just end up with the circle again. Okay, and we see that this eccentricity value here will range from 0 up to 1. Okay, not including 1, because in that case we will have a parabola. Okay, but it lies within that range. And different eccentricity values are responsible for different amounts of stretching of the ellipse. Okay, next we have a parabola that has an eccentricity value of 1. And then the equation is a bit different from what you're used to, but here it's y squared is equal to 4ax. Okay, and then we can swap x and y to have parabola going vertically, so something like this, or we can swap them around and have parabola going like that. Okay, so that's just swapping those values, but the form of the equation is roughly the same. Okay, so that is a parabola, and then the last one is a hyperbola. Okay, this has an eccentricity value similar to the ellipse, but instead of the minus, we have a plus. So this will be the square root 1 plus b squared over a squared. And we can see from this form that this eccentricity will be bigger than 1. Okay, so it will never get to 1, so it's not a parabola, but it's bigger than 1 and can go off to as large as you want it, and then that makes it a hyperbola. And the eccentricities look fairly similar to the ellipse, as well as the equation, so please don't confuse them. So in ellipse, the eccentricity is 1 minus b squared over a squared, and then we have a plus between those terms. For the hyperbola, it's 1 plus b squared over a squared, and then there's a minus between these terms. Okay, so there's a bit of switching around there, so please don't get confused between those two. Okay, and then as with the parabola, we can have the vertical ones or horizontal ones. We can have a similar thing for hyperbola. So this x term and the y term, we can swap those around. So we can have y squared over b squared minus x squared over a squared equals 1. And then that will also change from being a horizontally oriented hyperbola to a vertically oriented hyperbola. Okay, so roughly it will be something like this. Okay, so horizontally orientated to vertically orientated. Okay, so that's just a rough sketch. We'll go into more detail later on. Okay, so let's have a look at some features of these different shapes. So the first one being the circle, and we're going to look at the vertices and the foci. Okay, there are other things as well, like the major minor axis, the directrix, and so on. We won't be getting into that in this lecture, so please go through your notes for those geometric views. Okay, so for now we're just going to be looking at the calculations involved. Okay, so vertices and foci. Okay, so first the circle. Okay, so the circle doesn't have any vertices. We'll see that the ellipse does, the parabola does, and the hyperbola does, but the circle does not. Okay, and that's because of that symmetry. So you can go all the way around the circle, and no point is really different from any other one. Okay, so there's no vertices. We do have one focus, and that is the very center of the circle. So if we have a circle, the very center, we call that a focus. Okay. The reason we call it a focus is you can imagine horizontal light rays coming through. Okay, so this is just something to imagine. If you do optics, you'll see that this is studied when we look at circular mirrors and parabolic mirrors, but here you can just imagine it. So we have a horizontal light ray coming in, and then it bounces and goes through the focus. So we have something like that. So any light rays coming in goes through the focus, and so if we have light rays coming from some object, it will be focused at that point. In other words, we will have an image formed at that point. Okay, but again, you don't need to know that. That's just something to think about when you want to know what a focus is. Okay, so you can imagine horizontal light rays coming in, and they get focused at that point. Okay, we call it the focus. Okay, so circle, no vertices. It has a single focus at the very center. Number 2, an ellipse. Okay, an ellipse will have vertices and foci. So let's do a quick sketch of this. Okay, so it's something like that. You've got a circle and slightly stretched. Okay, just a quick note, this longer side here, we call that the major axis. Major axis. And then the shorter side we call the minor axis. Okay, and then half of either of those, that will be the semi-major or semi-minor. So if we cut it in half, it becomes semi. Okay, so the 2 endpoints along the major axis, those are the vertices. So over here and over here, that's the vertex on either side. And then we have a similar thing at the top and at the bottom here. So for the shorter side, it's not a vertex, it's a co-vertex. Okay, so that corresponds to the shorter axis. So those 2 endpoints there. Okay, and then the foci, that will be somewhere inside like that. Okay, so what happens is we take a circle with a single central focus. If we stretch the circle into an ellipse, then the focus gets split into 2, and they move left and right. So from one focus, we get 2 foci. Okay, so how do we calculate where these points are? If we have the equation, x squared over a squared plus y squared over b squared is equal to 1, then we can just read off the vertices, and there's a little calculation we have to do for the foci. So here, this is one of the foci, so it's a focus. Okay, so first of all, the vertices, so the horizontal ones, they will be located at minus a and plus a. So here we've got x squared over a squared, whatever that a value is, that will give us our vertices. So vertices plus minus a and 0. Okay, so that is if this ellipse is not shifted. So given this equation on the right, we have those as our vertices. If the ellipse is shifted left and right or up and down or some combination, then the vertices will shift with it. Okay, we'll look at that at the end. Okay, so those are the vertices, and then what about the foci? So these are located at f1 and 0 and f2 and 0. So there's 2 of them, unlike for the circle where there's just the 1. Okay, how do we calculate these? So f1 is just plus a times the eccentricity. Okay, that's pretty easy to calculate. And f2 is minus a times the eccentricity. So we have the symmetry as expected. Since the shape is symmetric, we expect that we get mirror images of the vertices and the foci. Okay, so these 2 here, we could write this as plus or minus a, which is from the equation, and then e, that's the eccentricity, and 0. Okay, so those are the vertices and the foci of a ellipse that hasn't been shifted anywhere. Okay, so it's centered at the origin. If we do have a shifted ellipse, then the vertices and the foci will also be shifted. So just a note on a shifted ellipse. So let's write a general form where we shift it horizontally as well as vertically. If it is only shifted horizontally or only shifted vertically, you can adapt it for what's given. But in general, we have x minus h squared over a squared, so horizontal shift there, and then we can have y minus k squared over b squared is equal to 1. That gives us our vertical shifting. Okay, so how does the foci change? So f1, this is going to be replaced with h plus a times the eccentricity. So the previous value of a, that's being moved over by h, since that is our shift in x. Similarly for f2, for the second focus, that's going to be h minus a, again times the eccentricity. Okay, so we need to account for those shifts. Okay, and then that's shifted horizontally. If we want to account for the shift vertically, we know that both of these foci will lie along this line, okay, this horizontal line. So if we have any vertical shifting, then this horizontal line is just moved up with the shift. So that's very easy to take into account. So we're going to have f1 and k, since we're shifting by k, and then we're going to have f2 and k, again, because we're shifting by k. Okay, and I'm going to leave the vertices as a homework problem. Okay, so homework problem. Find what happens to the vertices for a shifted ellipse. Okay, so it's very easy to do. We just need to find the points prior to the shift and then think about what happens to those points after the shifting. Because if we shift an ellipse horizontally and then vertically, every point within the ellipse and on the ellipse will move accordingly. So if we know the points before, what happens after? Okay, so very easy. So I'll leave that for homework. Okay, so that's it for the ellipse. Again, if you want to look at the full geometric picture with the directrix and so on, please look in the notes. Okay, so that's the full definition of an ellipse based on the foci and having fixed length to the circumference and so on. I won't be covering that now because that is available in the notes. Okay, so please read through that. Okay, the next thing is the parabola. Okay, so the parabola has a single vertex and a single focus. So I'll draw a quick diagram. So let's say we have a parabola like this. We're going to have a single vertex at the turning point. Okay, so single vertex at turning point. Okay, it's very easy to calculate the turning point. We just need to complete the square. If you do need any help with that, please just send me an email and I can help you with that. Okay, so if you struggling with calculating the turning point of a parabola, please just let me know. Okay, so that's the vertex or the turning point, and then the focus is somewhere just above here. So this is the focus. And again, you can imagine the same thing like we did with the circle. If you think about the light rays coming in, so here we have vertical light rays coming in like this. They will bounce off. If we imagine this as a parabolic mirror, they'll bounce off and then go through the focus. Again, that's why it's called a focus. Okay, and then we'll go through like that. Okay, so any of these light rays coming down vertically that are parallel to the vertical, they will bounce off and go through the focus. And again, you don't need to know that. It's just something to think about to understand what the focus is all about. Okay, so what is this focus value? If the parabola is centered at the origin, like your y equals x squared standard parabola, then the focus is at A. So the focus is F, and it has the value A. Okay, so that's from the equation. So remember, we have the y squared is 4ax, or if we swap it around or view it either vertically or horizontally, we can write this as x squared is 4ay. That a value, that gives us the focus. So if this again is centered at the origin, then this will be at A0 if we are shifting left or right. Okay, so if the parabola looks like this, or 0A if your parabola looks like that. Okay, and there's the focus there. So it's either along the x-axis or it's along the y-axis. Okay, so that is where the focus is. And again, the vertex, that's just the turning point. Okay, and remember, when you're finding the focus of a parabola, it needs to be in this standard form here. Okay, so remember there's that extra factor of 4 that we need to take into account. Okay, and as with the ellipse, if we take this parabola and shift it horizontally and or vertically, then the focus and the vertex will shift in accordance with that. So if we shift the parabola vertically or you can do both, and or horizontally, then the focus and the vertex also shifts. Okay, so something like y minus k is equal to 4ax minus h squared. Okay, so here we've got a shift in y due to the k, we've got a shift in x due to the h. So whatever vertex that we found, we also need to take into account this shifting. Okay, so that's the parabola, and then lastly we have the hyperbola. Okay, so the hyperbola, similar to the ellipse, will have 2 vertices and 2 foci. So there's 2 forms of the hyperbola. So we have the x squared over a squared minus y squared over b squared is equal to 1. This is the horizontally oriented hyperbola, so it looks something like that. Okay, and then we have another one, which is y squared over b squared minus x squared over a squared is equal to 1, and that is something like that. Okay, so sketching these is not so bad. We will have a look at that later. But for now, if you want to get an idea of what these look like, So if you're doing the tutorials and you're unsure of what you're working with, please have a look at the website Desmos. Okay, so it's a free online website that you can use to plot these graphs. Okay, so all of these equations that we've looked at, try and plot them in Desmos, change the values around, and see what kind of shapes you get. Okay, and then along with plotting those shapes, also plot those points. Okay, so the vertices and the foci, and see how they also change if you change these values of A and B. Okay, so again, just have a look at Desmos for the curve sketching. Okay, so those are the two kind of shapes that we get, horizontal or vertical. I'm just going to go through the horizontal one, but the vertical one is very similar. Okay, so let's say we have a horizontal one, so it's something like this. Sorry, let's draw that a bit better. Okay, something like that. We've got two vertices over here and over here. So in the horizontal case, where we've got them opening up left and right, these are just the x-intercepts. So here the vertices are the x-intercepts. Okay, if we were dealing with the vertical picture, then the vertices would then be the y-intercepts. Okay, but this is only if it is not shifted. If we have a shifted hyperbola, then these will, of course, shift with it. Okay, and then the foci, that's somewhere here and somewhere here. Okay, so the vertices, again, in the horizontal picture, those are given by the points minus A and 0, and then on the other side, A and 0. And that just comes from the equation. So x squared over A squared, that A value, that determines the vertices. And again, if this is shifted, so if we shift it horizontally or shift it vertically, then the vertices will shift with it. Okay, so please keep that in mind. If anything is shifted, then these vertices and foci will also shift. Okay, so those are the vertices. What about the foci? So here, that's one focus, and then on the right we have the other one. Those are given by F1 and F2, same as before. So F1, that will be plus A times the eccentricity, and F2, that will be minus A times the eccentricity. Okay, and then these give us the 2 points, F1 and 0, and F2 and 0. Okay, so again, that is for the unshifted hyperbola. If the hyperbola was shifted, then these focal points here, they will also be shifted. Okay, depending on how you shifted the hyperbola. Okay, so let's have a look at what happens if it is shifted. So a shifted hyperbola, hyperbola. Okay, so in general, we can shift it horizontally or shift it vertically. And then also keep in mind that we can have a horizontal type hyperbola or a vertical type hyperbola. Okay, so let's look at the first one. We have x minus h squared over a squared minus y minus k squared over b squared is equal to 1. Okay, in this case, we're going to have the foci at the points h plus minus c, and then shift it up so we go to k. This c value, that comes from simplifying f1 and f2. So if you just substitute the eccentricity that we mentioned right at the beginning, we'll see that c squared is a squared plus b squared. Okay, so you can just look at the eccentricity formula, substitute it into F1 and F2, and then we'll see we get this, this value C. Okay, and H, that's the horizontal shift, and K, that is the vertical shift. Okay, if we have the other type of hyperbola, so y minus k squared over b squared minus x minus h squared over a squared equals 1. Here we need to swap around the shifting. So this will be h for the horizontal shift, and then we shift the foci up and down, okay, because they will be vertically orientated. So that will be k plus or minus c, the same c as before. Okay, and then the vertices will also shift accordingly. Okay, so please have a look at that Desmos. Okay, so please plot these with different values of a and b, different values of h and k. Also plot the vertices and the foci to see how they are affected by different shifting. Okay, so we will look at this later on, but please just in your own time now go on to Desmos, plot these, and see what happens when you change the values. Okay, as always, if you have any questions, please just send me an email and I can help you out. Okay, so the tutorials are up. I will also post the solutions so you can check your work. If you have any issues with that, please just send me an email. Okay, I'll see you next time.